Hi guys, what's going on, smart people? In this opportunity, we are going to resolve the third part for this problem, the part C. So the problem says a particle of mass m moves in a central force field with potential V. The Lagrangian in terms of spherical polar coordinates is shown, is given here in the problem. So part A, find the momenta, we did already. Part B, find the Hamiltonian, we did. And part C, write down the Hamilton's equations of motion. So that's the part we are gonna resolve. Okay. The Hamilton, by definition, the Hamilton equations, so part C would be Hamilton equations of motion are by definition the following. The Hamilton equations of motion are by definition the following. dr or dq I with respect to time equal to dh dpq. Okay, and dp I dt equal to minus dh dqi. So in these equations, q, where here qi and pi represents the generalized coordinate and momenta respectively. And momenta respectively. Okay. Well, if we start solving or finding the Hamilton's equations for the Hamilton's equations of motion for the first coordinate, in this case the first coordinate is the radial, so we start solving the equations for the radial. We know, okay, before that we have to remember that the Hamiltonian is PR square dividing 2m plus p theta square dividing 2m r square plus p phi square dividing 2m r square sine square of theta plus the potential VR. If you remember, we calculated the Hamiltonian in the last video. Okay, guys? So, in order to find the Hamilton's equations of motion, we are going to start using the equations. We can enumerate these equations as 1 and 2. Okay, we can enumerate these equations as 1 and 2. We can enumerate the Hamiltonian as 3. All right, so number 3 equation. We start with the coordinate r. Okay, so if we start with the coordinate r, sorry, equations number 1 and 2, they are gonna be like dr dt is equal to dh dpr, and the pr dt is equal to minus dh dr. All right, so we are gonna calculate these two equations, this equation and this one. All right, well, okay, let's do it. dr dt is equal to dh dpr, and that's equal to, okay, let's see, the Hamiltonian is dpr, Hamiltonian is, okay, I am replacing the Hamiltonian here, right here, so it's going to be pr square dividing 2m plus p theta square dividing 2m r square plus p phi square dividing 2m r square sine square of theta plus phi r. If you see, we are gonna derivate with respect pr, so the terms which are not depending of pr, the derivative is gonna be 0. So this one is gonna be 0, the derivative, and this one too, and this one as well. Okay, then we get the following. We get that dr dt is equal to, okay, derivative with respect pr of pr square dividing 2m, the derivative of pr square is 2pr, all right, and you know 2m is constant, so it won't change, so we get 2pr dividing 2m, and these 2 and the 2 on the this 2 cancels with this 2, and we get pr dividing m. So the first equation is dr dt is equal to pr dividing m. That's the first equation of, or the first Hamilton's equation. Okay guys, this is the first equation. We can do something like this. This equation, if we write dr dt, if we write dr dt as r dot, you remember that we can use this convention for derivatives, so we can write the equation like r dot is equal pr dividing m, and if we clear pr, we get r dot multiplying the mass, or the mass multiplying r dot is equal to PR. And this is the momenta for a particle that is moving with a certain velocity. Okay, so this is a equation. Basically, this equation has this like this. Basically, this equation is like v equal PR, and is the conventional equation for momenta, linear momenta. So we can see here that the coordinate r is changing with respect to time. Okay, well, so we have this solved. We go now to the other equation, that is, we go now to dpr dt. dpr dt is equal to dpr dt is equal to minus partial derivative of the Hamiltonian with respect to time, with respect to the coordinate, in this case is r. Well, we know that this is going to be the derivative with respect minus derivative or partial derivative, in this case with respect r of the Hamiltonian, PR squared dividing 2m plus p theta squared dividing 2m r squared plus p phi squared dividing 2m r squared sine squared of theta plus VR. Okay. In this case, guys, okay, let me to have more space here, plus VR, and that's equal to, okay guys, is the derivative or partial derivative of the Hamiltonian with respect to the coordinate, in this case r. So if you see we have r here, we have r here, we have r here. These two terms are depending of the radial, and this one too. So what we can do is, I will do it directly. I'm gonna move the terms which are on bottom, like this one and this one. I'm gonna move them to the top, okay? But when I do that, I have to change the sign of the power, okay guys? So when it is r squared on bottom, it's gonna be r minus squared on top. That's a simple rule of powers, okay guys? And the same for the other term. On the bottom is r squared, so on top is gonna be r minus squared. So that's what I did. Now when I resolve the derivative, the first term is gonna be the derivative of the first term of this one is gonna be 0, because that term does not depend of the term r. Okay, so that one goes away, it disappears. The second term is gonna be, so we have minus, is this sign, okay, minus the derivative of p, and in this case p theta dividing 2m is going to be a constant. P theta squared dividing 2m is going to be a constant. Okay, the derivative of r minus square is going to be minus r minus 3, okay, plus this one is constant, okay, the same for this one is constant, the one I am getting into the parentheses, p theta square dividing dividing 2m sine square of theta. Okay, the derivative of r minus square is minus r, okay, minus 2 minus 3 r, minus 2 r minus 3. I forgot to write the minus 2 over here, so it's gonna be minus 2. No, sorry, this one, this minus 2 r minus 3, and the same here. And the next term is the derivative of VR is gonna be my plus derivative of VR with respect r, and it's gonna be an implicit term because we don't have the explicit form for the potential. So what we get here is these two cancels with this, okay, these two cancels with this. When we distribute this minus sign into the bracket, minus with minus is plus, minus with minus is plus, minus with minus is plus, and minus with minus is minus. Sorry, minus with plus is minus. Well, we get the p r dt equal to finally p theta square, this term that is on top with minus 3, power minus 3, I gonna do the same as we did in the last step. I gonna take them back to the bottom, so the power is gonna be positive in this case. PR p theta square m r square cube plus p phi square dividing m r cube sine square of theta minus derivative of BR with respect R. And this is the second equation. This is the second equation. Okay, now we go to theta. Now we go to theta. With theta. So the first equation is the theta dt is equal to the h partial derivative of the h with respect to p theta. So, but if we go to the Hamiltonian, we know that the only term depending of theta, p theta, is this. Is this. So when we do the derivative with respect p theta of this of the Hamiltonian, the first term, the third term, and the fourth term, they go away. They disappear because the derivative with respect p theta of those are 0 because they don't depend of theta. The only term surviving is the second one, p theta squared dividing 2m r squared, the one highlighted. So we are gonna get p theta, this is equal to the h with respect to theta, but h in this case is p theta squared dividing 2m squared. I don't write down the other terms because for the Hamiltonian, because they disappear, they are 0, the derivative for those ones, okay? So it's pointless to write a lot of terms that they are going to be 0. So that way we save time. Well, the derivative of p theta with respect of p theta squared with respect to p theta is 2p theta. So this one is going to be 2p theta, 2p theta dividing 2m r squared. 2 cancels with 2. With 2, I get p theta dividing m squared. And this is the second equation. Sorry, this is the first equation for theta. The theta dt is equal to p theta dividing m r squared. Okay, guys. Now we go to the equation, the second equation of Hamilton for theta, and that one is dp theta dt equal to minus h dh d theta. Well, we get minus dh minus derivative with respect theta equal to, okay, here if we check the Hamiltonian real quick, we are gonna see that the only term depending of theta is this, the third term. Okay, so I only gonna write down this one. I won't write the other ones because the derivative of those other terms with respect theta is gonna be 0 because they don't depend on theta. So the only term that is depending explicitly of theta is this one. So I'm gonna write only that term, and we are gonna get something like this. The derivative with respect theta of p theta squared dividing 2m r squared sine square of theta. Okay, guys, what I'm gonna do is I'm gonna write sine squared on top, and I'm gonna change the sign of the power. So we're gonna get derivative with respect to theta equal to p theta squared sine minus square of theta dividing 2m r squared. Okay. And to continue doing this is the p d theta with respect to time is equal to minus derivative with respect to theta of p theta squared dividing 2m r squared, in this case sine minus theta minus square of theta. Okay, the derivative of, in this case, is gonna be we can write this like this. We can write this like, I'm gonna write this like this. Take care, pay attention to what I'm gonna write. I'm gonna write sine of theta minus square. Okay, and I'm gonna do the derivative. In this case, it's gonna be like, okay, these terms are constant. Okay, p theta squared dividing 2m squared r squared, those are negative. Sorry, those are constant. Okay, so it's gonna be, I keep this sign, minus sign, out of the parentheses or the crochet, sorry, the brackets. So it's gonna be p theta squared dividing 2m r squared. But the term sine of theta, I'm gonna derive that one. So the derivative is gonna be minus 2 sine of theta power minus 3. That's the external derivative. Okay, that's the chain rule. The external derivative and the internal derivative is gonna be cosine, because derivative of sine is cosine of theta. And that's it. Okay, so this term, this minus with this minus, minus with minus is plus. So the term is going to be plus final, and this is going to be p theta squared. Okay, this sine theta minus 3 power minus 3, I'm gonna send it to the bottom, and I'm gonna change the sign of the power. So on the numerator, I'm gonna have only cosine of theta dividing these two and these two, they cancel each other, and I'm gonna have on the bottom m r squared sine minus 3 of theta. So finally, this equation is gonna be dp theta dt equal to p theta squared cosine of theta dividing m r squared sine minus 3 of theta. Okay, guys, that's it. The last equation is gonna be the last two equations for now. We work with phi. Okay, guys. This is real quick. I'm gonna do it real quick here. So the phi, the first equation is gonna be the phi dt, and it's gonna be the h, the phi. But if we check the Hamiltonian, the only term that is depending of phi, here is p phi. The only term depending on phi is this, the third one, and the derivative with respect phi, with respect p phi, is 2 p phi, dividing the terms on the denominator on the bottom. So it's going to be really easy because I only apply the derivative on this term and the rest of the term is constant. Okay, so I will have p phi dividing m r squared sine square of theta. Okay, 2 dividing 2, and this 2 cancels with this as well, and I get this finally. And the p phi dt is equal to minus the h the phi. But if we check the Hamiltonian does not depend on phi at all, so the derivative is going to be 0. Okay, guys, and what does this mean? Okay, this means that phi is a constant of motion. Okay, guys, this is the problem. So hopefully you like my explanations. If you like, please give me a like and subscribe to the channel. Don't forget to share with your friends, and see you in a next video. Bye.